Here's a question. You are given an ice cream cone and a cup of tea and asked to determine which one of the given items is hotter. Obviously, you would touch and feel both of them and come to the conclusion that the tea is hotter. Now, what if you are not allowed to touch the given items? Still, your common sense will tell you that the tea will be hotter than the ice cream. But now, you are presented with two cups of tea. One of them is slightly hotter than the other. How do you choose the hotter one? We are very familiar with the word temperature, but what exactly does this term mean? Temperature is a marker for the hotness of a body. When two bodies are arranged in such a way that they are in thermal contact, the direction of the flow of heat is determined by the physical quantity of temperature. Heat flows from a body of higher temperature to a body of lower temperature. And according to the zeroth law of thermodynamics, the heat flow stops when the two bodies attain the same temperature. Now, consider a system A which contains billions of particles. These particles have three kinds of kinetic energies due to their translational, rotational and vibrational motions. So more specifically, the temperature of a system can be defined as a measure of the average kinetic energy of the particles in a system. Now, in addition to the kinetic energy of the particles, they also have potential energy by virtue of their intermolecular bonding. The sum of the kinetic energy and the potential energy of these particles is termed as the internal energy. This internal energy is denoted by the letter capital U. But let's say that the particles of the system are kept in a container and the container is moved. For example, you put this container inside a car which is going 100 miles per hour. Then the system has kinetic energy which is not associated with the internal energy of the system. The kinetic energy component in internal energy of the system is referring to the energy possessed by the particles in the system due to their random motion. So if you put this container in a car going at very high speed, it will have no effect on the temperature of that container because we are not changing its internal energy. Thus, internal energy is a quantity that is linked with the atomic motion inside the system and is directly proportional to the temperature of the system. The higher the internal energy of the system, the higher is its temperature. So here we have a summarization of what we have done so far. We have warmer objects, we have cooler objects. The warmer object has more internal energy, the cooler object has less internal energy, and when they are in thermal contact, we have heat transfer until equilibrium is obtained. Now, consider a gaseous system in a container. The container is connected to a movable piston, and there are two ways to change the internal energy of the system. Number one, we keep the container in a contact with a hotter body. Due to the temperature difference, there will be heat flow from the surroundings, that is, the hotter body, into the container. Otherwise, we shall move down the piston and compress the gas ourselves. This will also result in a change in its internal energy. The reverse is also possible. For example, if the system is kept in contact with a colder body, the heat flow from the system to the surroundings. Also, if the piston is massless, the gas can work on the surroundings and move the piston. Therefore, we can say that heat and work are two modes which will change the internal energy of a system. Now, how do we describe this in mathematics? We do this using state variables. State variables represent the thermodynamic state of a system. The values of such variables only depend on the given current state of the system and not on how that state was achieved. That is, how the system achieved that particular state is simply not a factor. Internal energy is a macroscopic state variable, just like pressure or volume or temperature. On the other hand, work done and heat energy are not state variables. They are modes of heat transfer to a system which change its internal energy. They are both path-dependent variables. What does that mean? Let us say we have a system A which over time shifts to system B. Now, there are two ways we can achieve this. We can either go by a long route. There are many different states in between, many changes in the internal system before we get to B, or we can do this in a single step. In the case of the internal energy of the system, the state variables, they will not care which route you took to get from A to B. On the other hand, things like heat energy will depend on the specific path you use to get from A to B. The amount of heat gained or lost by the system is constantly changing here, and that is why they are not considered state variables. However, the final internal energy of the system B does not care how the state was reached, but only on the final value of the state variables when the system reaches state B. Now let us summarize what we have done so far.
Manorama Horizon. Learning made simple.